In this video, we are going to talk about empirical formulas, molecular formulas, as well as percent yield, actual yield, theoretical yield, and limiting reagent. So the empirical formula for a compound is the simplest whole number ratio of ions, atoms for each element in a molecule. So for example, for this molecule called benzene, the formula is C6H6. This is the molecular formula. So it's composed of 6 carbon atoms and 6 hydrogen atoms. Now, this doesn't tell us anything about what it looks like or how it's bonded, but that is the molecular formula. Now, notice that both of these subscripts are divisible by 6. So 6 divided by 6 is 1 for carbon, and 6 divided by 6 is 1 for hydrogen. So we can divide both of those by their common factor, essentially, and we get just 1. So we don't normally write the ones for subscripts, but that gives us the empirical formula. So the molecular formula is C6H6, and the empirical formula, we're just simplifying it a bit, and we get CH. Another example, octane, the formula for octane is C8H18, and notice that both of these numbers are divisible by 2. So 8 divided by 2 is 4, and 18 divided by 2 is 9. And then those are not also divisible by some common factor. Like they're both not divisible by 3, they're not divisible by 2. So that tells us that our empirical formula is C4H9. So we've reduced it to the simplest whole number ratio. Another example, so C6H12O6. So that is the formula for glucose, a sugar molecule. And notice that all 3 of these subscripts are divisible by 6. So 6 divided by 6 is 1, 12 divided by 6 is 2, and 6 divided by 6 is 1. So the empirical formula for sugar would be CH2O. Another example, so NH3, that is the formula for ammonia. Now, we've got a subscript of 1, essentially, and a subscript of 3. Now, those are kind of already simplified, so 1 and 3 are not both divisible by some number. So NH3 is the molecular formula for ammonia, but it's also the empirical formula because it's already down to a simple whole number ratio. So it is possible for the formula of a compound to be the molecular formula and the empirical formula. Now, calculating the empirical formula, we can do that if we're given composition data. So essentially data on the mass or the mass of the reactants, mass of the products, and we're going to do a couple examples to explain how that works. So for example, if we want to determine the empirical formula of radium oxide, we do this experiment, and we see we had 1.64 grams of radium metal, and then it's heated, and we end up with 1.755 grams of radium oxide. So the mass increased. And let's talk about what's going on really quick. So we have radium, solid metal, and it's heating, and it's picking up some oxygens. And the whole point is we don't know what the formula is. So they've got these question marks here. So I'll keep doing the question marks. We don't know the subscripts, and that's the point of this exercise, to figure out is what are those subscripts. Now, if the radium is reacting with oxygen, then it's probably reacting with diatomic oxygen gas. So that's our chemical reaction. Now, one thing to remember is law of conservation of mass, meaning the mass of the products is equal to the mass of the reactant. So reading the question one more time, they say that we have 1.64 grams of radium metal. So that's the mass here, 1.64 grams. And then we produce 1.755. So that's the mass over here, 1.755 grams of product. So law of conservation of mass says that the mass of the products must equal the mass of the reactants. So we can just subtract the two numbers to figure out the mass of the oxygen. Now that's just step 1 for solving these types of problems, but we need to know the mass of the 2 elements that are in their formula, or the mass of all 3 if there's 3 elements. And then essentially what we're going to do, and this is the rest of the problem on this next slide, is convert those masses to moles. So if we're going to try and find the mole ratio, then you need to know how many moles of each element you have. So from the problem, we had 1.64 grams of radium metal, and looking at the periodic table, we can get the molar mass for radium. We put the 226 value on the bottom so that grams would cancel, and now we have units of moles. And then for the oxygen, we have the 0.115 grams. We look at the periodic table for the molar mass of oxygen, and we get 16, and we put the 16 on the bottom so that the grams cancels, and we get 0.00719. So then the next thing that you do to figure out what is the mole ratio, because we are looking for integer values. I mean, we never have a compound where it's like radium 2/3 and then an oxygen 1/5. You know, it's never something like that. They're always whole numbers, like 1, 2, 3, 4, whatever. What we do is we figure out which one is the smallest number and divide both of those by the smallest number. So this is the smaller of the two. Got 0.00726 and 0.00719, so the oxygen one came out smaller. So we divide both of them by that, so oxygen will obviously come out to be 1 exactly. The radium, doing the 0.00726 divided by 0.00719, it comes out to 1.01. And then after that, we can round to the nearest whole number. So it would just be 1 radium, 1 oxygen, or we just write it as radium and oxygen. So RAO would be the empirical formula. We could also use percent composition data to calculate the empirical formulas. So we're going to run through an example that explains what we mean by that. And they're mass percent compositions. So in this example, it says acetylene is 92.2% carbon. So this is 92.2% by mass is carbon. And then 7.83% is hydrogen. So a trick for these problems is just go ahead and assume you've got 100 grams of sample. Even if they don't tell you the mass of the sample and they just give you percentages, just go ahead and assume you've got 100 grams of sample, because then you can quickly say, oh, if I've got 92.2% carbon, that means I have 92.2 grams of carbon, because 92.2% times 100 grams is the same thing as going 0.922 times 100 grams equals 92.2 grams. So we got 92.2 grams of carbon and 7.83 grams of hydrogen. So next, we can take these values and, like we did with the previous problem with the radium oxide, is convert them into moles. So here's the 92.2 grams, and we're converting into moles. So we use the molar mass of carbon from the periodic table, set it up so your units cancel, and we get 7.68. Same thing for the hydrogen. It was 7.83 grams of hydrogen, so we took that percentage and made it a grams. We divide by the molar mass, and we set it up so that the units cancel, and now we have moles, and we get 7.75. Next, which one's smaller? So 7.68 and 7.75, this one's smaller. So you do 7.68 divided by 7.68 for the carbon, and that's going to be 1. And then you do 7.75 divided by 7.68 for hydrogen, and it looks like that's going to come out to about 1.01, really, really close to 1. So since we get two numbers that are really close to 1, same thing, the empirical formula is just C1H1 or CH. Now, if you have a little bit of more information, a little bit of extra information in the problem, you can also get the molecular formula. And molecular formulas are always some multiple of the empirical formula. So if the empirical formula is CH, that means the molecular formula could be C2H2 or C3H3 or C4H4. But you'd have to know a little bit more information about the problem to figure out, okay, which one's the correct answer. And in problems, they'll do that by giving you the molar mass of the compound. So for acetylene, we figured out that the empirical formula was CH, and then the problem tells us that the molar mass is 26 grams per mole. So one way you can solve this is figure out the the mass, essentially the molar mass of the empirical formula, so a C plus an H, so that's 12 for carbon, plus 1 for hydrogen, and that's how we got the 13. And then divide that with the molar mass that was given, which was 26. So we basically got 26 divided by 13. Well, 26 divided by 13 is 2. So that tells us that this multiplier is going to be 2. So we would take the subscripts, C1, H1, and multiply both of those by 2 to get C2, H2. Let's say that the molar mass was 52 grams per mole. That means we would want to do 52 divided by 13, and our multiplier would be 4, which means that the formula would be C4H4. Now that's not a real molecule, but that's just an example of how it would work if you had a different molar mass. C4H4, I just made that up. So next up, limiting reactants. So what do we mean by a limiting reactant? So let's just pretend, let's say we're making some grilled cheese sandwiches. So to make a grilled cheese sandwich, I mean, unless you like really, really love cheese, you take 1 slice of cheese and 2 slices of bread. So 1 piece of cheese and 2 slices of bread makes a sandwich. So what if you've got 5 slices of cheese and 8 slices of bread? How many sandwiches could you make? So you have enough bread for 4 sandwiches and enough cheese for 5 sandwiches. So how many sandwiches can you make? Well, the bread is kind of limiting how many sandwiches you can make, so you can only make 4 sandwiches. So you're going to run out of bread first before you use all the cheese, and you'll have an extra slice of cheese. So we would say that the bread is limiting and the cheese we have extra of. So since we're going to run out of bread first, bread is what we would call the limiting reactant. So the ingredient that limits how much product you can make is the limiting reactant. And then any other reactants are going to be the ones in excess. So key idea is that a limiting reactant is the one that's going to be used up first. It's going to run out first, and then all the other reactants are in excess. You should have extra of those when you're all done, just like we had 1 extra piece of cheese. So as an example with an actual chemical reaction, let's say we've got 2.5 moles of iron and 3.00 moles of sulfur. How many moles of product would be formed? So we have this iron to sulfide product. Now, according to the balanced reaction, we've got 1 mole of iron reacting with 1 mole of sulfur to give 1 mole of product, because all of these have a 1 coefficient in front of them. So let's just pretend that the iron is the limiting. Since they all are in a 1 to 1 to 1 mole ratio, 2.5 moles of iron would react with the same amount of sulfur and produce the same amount of iron sulfide. So 2.5 moles, 2.5 moles, 2.5 moles. Well, we have 2.5 moles, and according to this, it's saying we would need 2.5 moles of sulfur, but we've got 3 moles of sulfur, so we've actually got more. So the sulfur is what's in excess, and then the iron, I'll write LR for limiting reactant. So the iron is the limiting reactant, the sulfur is the one in excess. So to kind of like put this in a table, because quite often with problems like this, it's really helpful to have a table where you've got the before and the after, or maybe even the before, what's changing or what's reacting, and then after. But we had 2.5 moles of iron, and we had 3.00 moles of sulfur, and before the reaction, we didn't have any of the product. That should be a lowercase e, by the way. Now, afterwards, if the iron is the limiting reactant, then that means we're using up all of it. So there's none left. We ran out. But the sulfur, we used up 2.5 moles. So then 3.00 minus 2.5 is 0.50. So this 0.5, that's how much is left over. And then we make that same amount in iron sulfate. So we make 2.5 moles of the iron 2, not sulfate, sulfide, but we make 2.5 moles of it. So there's basically 3 steps to figuring out a limiting reactant problem, and there's actually different ways to do this. So this is just one strategy, but I'll explain how you could simplify this a little bit. But number 1, calculate the mass of product that can be produced from one reactant or the first reactant. And honestly, you could also do it for the moles of product. So they've got you going from moles of product to mass of product, but you could also figure out the limiting reactant by just going to the moles of product. But assuming you've got 2 reactants, so like reactant A plus B makes C, you have to figure out from the amount of you have of A, how much of C could you make? And then step 2, you do the same thing for the other reactant. Starting with B, however much you have, figure out how much of C you would make. And then the limiting reactant is the one that produces the less amount of product, so the least product. Whichever one gives you a smaller answer, whichever one yields the least product, that's your limiting reactant. So I'll do a quick example. How much molten iron is formed from the reaction where we have 25.0 grams of iron to oxide and then 25.0 grams of aluminum. So here's our balanced reaction. So first up is we're going to do it where we take each reactant and figure out how much product we would make. So first we're going to figure it out from the perspective of iron 2 oxide and figure out how much iron we're going to make. So they start off with the mass that we were given of the iron 2 oxide, and then this first conversion is converting into moles of iron oxide, so they're using the molar mass that they calculated, setting it up so grams cancels. Next up, the second conversion is the mole to mole ratio to go from the iron 2 oxide to the iron. So we've got a 3 in front of both of those, so that's why it's 3/3. And they set it up so the units, moles of iron oxide, cancels. And then the last conversion is they're using the molar mass of iron to convert it into grams of iron. So assuming that iron oxide was the limiting reactant, we would get 19.4 grams of iron. So that's one of it. We got 19.4 grams if the iron 2 oxide was limiting. So now let's do it again, but from the perspective of the aluminum. So the problem said we had 25 grams of aluminum. We're going to first convert into moles by using the molar mass of aluminum. So grams will cancel. And then we're using the mole to mole ratio to go from aluminum to iron. So we've got a 2 and a 3. So that's why we have a 2 on the bottom and a 3 on the top. And we set it up so moles of aluminum cancels. And then last, we're using the molar mass of iron again to convert from moles to grams, and we have 77.6. So if the aluminum was the limiting reactant, then we'd make this much iron. Now we compare the 2 answers. So first, assuming that the iron oxide was limiting, we got 19.4. Then if we assumed aluminum was limiting, we got 77.6. So notice that we started with the same mass. These 2 reactants had the same mass, but they have different molar masses, so we end up getting different results here. These 2 reactants had different molar masses, and there was a different mole to mole ratio to go from reactant to the product. But we've got 2 different answers. That one, the 19.4, gave us a smaller answer, so that tells us that the iron 2 oxide was limiting, which means the aluminum must be the one in excess. We can also do limiting reactant problems involving gases. So we would just use the volume of the gases, and it's going to follow the same procedure because the moles of gas is proportional to the volume by virtue of the ideal gas law. So PV equals nRT. There's several gas laws that we've talked about, and the ideal gas law kind of sums all of them up. So just to kind of review, P is pressure, V is volume, N kind of stands for number of particles, but it's really the moles of the gas. R is the gas constant, so it's just a number, and then T is the temperature, specifically in kelvins. But the volume of the gas is proportional to the moles, and specifically if we're talking about a gas at standard temperature and pressure, which is 273 Kelvin and 1.0 atmospheres for the pressure, then 1 mole of gas equals 22.4 liters. The point is that moles and volume is proportional, so we can actually go directly from volume of reactant to volume of product. If we were to do the conversion like the long way, so to speak, converting from a volume of one gas, I'll call it A, and convert to moles of that gas, and then convert to moles of the other gas, maybe the product, and convert back into a volume, we would end up using the 22.4 factor twice, where one time we're multiplying and one time we're dividing, so it kind of cancels each other out. So the point is that we can just kind of shortcut it and go directly from volume of reactant to volume of product for these limiting reactant type of problems. So let's do an example to see what that looks like. So the problem says how many liters of nitrogen dioxide gas can be produced from 5.00 liters of nitrogen monoxide gas and 5.00 liters of oxygen gas. So here's our balanced chemical equation. And one important thing to note is the mole to mole ratio. So what this is saying is 2 moles of NO gas react with 1 mole of oxygen gas to produce 2 moles of NO2. And if, in case you're curious, this UV over the arrow just means that ultraviolet light is needed to kind of get the reaction started. So what we'll do is we'll convert liters of NO, so that's one of our reactants, to liters of product, and we'll do the same thing for oxygen. We'll convert the liters of oxygen, so it's 5 liters, and we'll convert that to product and see which one gives us the smaller result, because that will be our limiting reactant. So for the nitrogen monoxide, we're starting with 5 liters. And then what we're doing here is using the mole to mole ratio from the balanced chemical equation. So is 2 moles of NO yields 2 moles of NO2. So that's why we've got a 2 over a 2 right here. And then the units are canceling out. Liters of NO cancels. So 5 liters of nitrogen monoxide would yield 5 liters of nitrogen dioxide. Same kind of thing for oxygen. We've got 5 liters of oxygen gas. We're using the mole to mole ratio to convert from liters to one thing of liters to another. So we're just looking at the coefficients. So the oxygen had a 1, so we've got a 1 in the denominator. The product had a 2, so we've got a 2 in the numerator. Units cancel, and now we're multiplying by 2. So 5 yields 10. So now comparing our two results, when we had 5 liters of one reactant, we've got 5 liters of product. And when we had 5 liters of the other reactant, we got 10 liters of product. So this one's smaller. So we say that one is the limiting reactant. We say specifically the NO is the limiting reactant, the nitrogen monoxide. And then with the oxygen, that one gave us a bigger number, so that one's in excess. So the O2 was in excess. Sometimes teachers or students write just XS. But NO is the limiting reagent, O2 is the one in excess. Now, percent yield, actual yield, theoretical yield. So when you perform any laboratory experiment, the amount of product collected is the actual yield. So you can think of it as how much did you actually make? I mean, you could have made so much, but maybe something went wrong. Maybe you spilled something. Maybe the reaction just didn't go all the way to completion. How much did you actually make? And then the amount of product calculated from a limiting reactant problem is known as the theoretical yield. So how much could you have theoretically made if all of the reactants were converted into products with no mistakes, no loss of material, nothing spilled, 100% atom efficiency, whatever? That's your theoretical yield. It's kind of like what could you have theoretically done, and this is what actually happened. Now, comparing the two is percent yield. So it's the amount of the actual yield compared to the theoretical. And this is how we calculate it. We'll do actual divided by theoretical. And then to make it a percentage, we will times by 100. So just a quick example. This one says, suppose that a student performs some reaction and they obtain 0.875 grams of copper carbonate, copper 2 carbonate, and then the theoretical yield that they calculated was 0.988. So we're not going to worry about how they calculated this theoretical yield, but they did that part of their pre-lab or part of their lab calculations. They got 988, but then when they actually did the lab experiment, they only collected 875. So to calculate the percent yield, we're just going to divide those two numbers. So you see we have the 875 number that was on top, the 988 number was on bottom, and then we multiply by 100 and we get 88.6%. Now, really, the percent yield should always be something lower than 100%. If you calculate something greater than 100%, either your calculation was done wrong, or maybe it was just some sort of experimental error, like maybe you didn't dry off all the water, you filtered something. That's a common thing. So we might have an experiment where we've got, this is a terrible little filter funnel I'm trying to draw, and we collect stuff, and we're collecting our product inside this filter paper, and we're pouring water in there to help filter it, and then we have to dry off the water. What if you didn't dry off the water before you weigh it? That's a common reason why you might end up with a yield that's greater than 100%. But ideally, they should be less than 100%, but as close to 100% as we can get if we can. So just to kind of summarize everything that we've seen in this, this chapter, in this video, I guess, the coefficients in a chemical equation give us the mole ratio. So that is the key if you want to convert from moles of one substance to moles of another. You need to use the coefficients, so the large numbers in front of each species, each chemical formula, and that tells you the mole to mole ratio to go from reactants to products, or pretty much any chemical species to another one. The coefficients can also give you the volume ratio. So if you're working with gaseous reactants, you can use the coefficients as well. And then we can convert moles or liters of a given substance to moles or liters of another one using the balanced equation as well. And again, the reason why that works is because at STP, for example, 1 mole of gas equals 22.4 liters. If we're not at STP, it's just a different number. I believe in the lab we saw room temperature was like 25.4 liters if it was about 25 degrees C. And then the limiting reactant, theoretical, actual percent yield. So the limiting reactant is the reactant that is used up first. So ultimately, how much product you can create is determined by how much limiting reactant you had. And then the other reactants are just the ones that are in excess. So you've got extra of those. The theoretical yield is how much you could theoretically make, and it's a calculation based on the limiting reactant. Actual yield is what really happened. It's how much you actually created, isolated, collected in the experiment. And then percent yield, you're comparing them. So it's a ratio of actual over theoretical multiplied by 100.